There, let me know when I have the thumbs up. All right, welcome. Good afternoon. Welcome to the C3I Digital Transformation Institute's colloquium series. Before we dive into the colloquium, just a quick reminder, the C3I DTI is on a mission to attract the world's leading scientists and to join in a coordinated and innovative effort to advance the digital transformation of business, government, and society. This colloquium series is part of that mission, and we are very excited to share with you this series today. The DTI is a consortium of a number of universities and a partnership with C3.ai and Microsoft. The universities are University of Illinois, UC Berkeley, Carnegie Mellon, MIT, Princeton, University of Chicago, and Stanford. And NCSA and Lawrence Berkeley Labs are also industry partners, or sorry, university partners. We have a very exciting colloquium series this winter and spring. Of course, starting today with the talk by Claire Donnat. Starting in 2 weeks from now, because there's actually an exciting announcement about next week. 2 weeks from now, we will go to Professor Bose about modeling and managing the spread of COVID-19. Watch your email. There will be an email, of course, inviting you for that talk. And as you can see, there's a very exciting series for the rest of the winter and the spring. So plenty of things to do during this time of the pandemic. Today, or before we go to today, next week, we have our inaugural 2021 Research Symposium on the Frontiers in Digital Transformation Science. It is a 2-day event where the grand winners from our inaugural call for papers will present their research, and there will be some additional fascinating talks. Make sure to tune in between 8 a.m. and 12 p.m. Pacific time. It's 2 days, so just between 8 and 12. In case you can't make it, we'll be recording these sessions, and as always, we'll post it on the website. Take a look at c3dti.ai events. All right, if you have to drop off during today's call, make sure to check out the YouTube channel, which you can reach YouTube directly or through our website. All right, now on to the fun stuff. Today's speaker is actually the winner of the C3AI COVID-19 Grand Challenge. This was a challenge organized and hosted by C3AI with a lot of input from the Digital Transformation Institute. And the team, we awarded a grand prize to 7 teams across the globe. It was an international competition. This is actually the winning team. Please take a look at the website if you want to see more information. Today's talk will be 40 minutes with a 15-minute Q&A. Please use the Q&A feature to ask your questions. You can upvote a question if you like the question. We will try to answer as many questions as we can during the talk or otherwise after the talk. So without further ado, today's talk will be a Bayesian hierarchical network for combining heterogeneous data sources in medical diagnosis applications to COVID-19. The talk will be given by Claire Donnat. Claire is an assistant professor at the Department of Statistics at the University of Chicago. So without further ado, Claire, the virtual floor is yours.
Hi, thank you, Mary, for the introduction. Let me just share my screen. Okay, I hope everyone can see. So yes, hi everyone. Thank you very much for the introduction, and thank you for giving us the opportunity to present here today our work. So my name is Donnat, and I'll be representing the team, so also consisting of Nina Mulan and Freddie Bunbury, so also in this webinar. And we're going to present our C3I Grand Challenge submission, which was mainly was trying to combine diagnosis for COVID-19. So perhaps to start off with a little bit of motivation and why we sort of embarked on this project. The simple sort of fact that everyone can agree on today is that with COVID-19, any return to normal is contingent on our ability of correctly determining and reducing the risk of an outbreak. So whether it's going back to school, allowing live events, public live events, or traveling, everything now sort of boils down to trying to measure the risk that is associated to these events and trying to reduce that risk. The main thing is that this is actually a very difficult task because especially in the light of like what we've learned about the disease. In particular, 16% of cases are asymptomatic. So, 50% of detection is said to occur prior to symptom onset. And even among people, there's actually a very high heterogeneity in their in people's exposure risks. So some people, for instance, work from home, where others are a healthcare worker working in the front lines of the pandemic. So this all yields sort of a lot of variability in people's sort of probability of catching COVID, and in the probability of also sort of being able to quarantine and stay at home when they need to. So in light of all of this, pretty much what we can say is that widespread testing takes on a role of critical importance in this whole context. And some studies have even shown that, by simulation mostly, that just even being able to correctly test and detect cases would be sufficient to sort of curb the pandemic without even the need for a vaccine. So it's really critical. In particular, in this context of widespread surveillance, an attractive solution, at least that we thought it when we sort of embarked on this project, was the potential of lateral flow immunoassays as a test. So lateral flow immunoassays are this little plastic box that you can see on the image here, and they're actually they're a very easy at-home test kit in a way. So what you have to do simply is collect a little bit of a sample. So whether it's blood, if you want to maybe test your immunity, or just a nasal swab, if you're testing your current infection status, and you put it in the well, and within minutes, you can actually read off the bands that you see on the image here, whether you've had COVID or you're currently infected. So it's really a cheap and easily deployable solution in that it's extremely easy to use. The results are within minutes, whereas you typically have to wait for days with RT-PCR. It's also typically much cheaper than PCR, at least according to the insurance grids. And it's also quite versatile. So you have a version, for instance, for testing your immunity, or a version for testing your current status of infection. So in this context, these lateral flow immunoassay tests seem like an excellent solution to the thorough and widespread COVID-19 surveillance requirements that we have. But the main sort of hiccup in this strategy is their accuracy. So although they're very scalable and affordable, since everyone can do them by themselves and so can repeatedly test themselves, these LFA tests suffer from vastly varying levels of sensitivity. With a peak as low as 70% on asymptomatic individuals, according to certain studies. So here in the picture, this shows LFA, so for antibody testing actually, and it shows the sensitivity, so the probability of being detected as having antibodies for COVID as a function of days after symptom onset. And as you can see, is if you do the test too soon, then actually your probability of being detected as positive for COVID antibodies is actually quite low. And so, since like when people test themselves, they usually do, try to do it quite fast. This actually hinders a little bit, the whole process. And actually, this accuracy is a huge concern. So, for instance, in England currently, they were trying to deploy LFAs for COVID testing, and they're always debating whether it's actually a good practical solution because of that accuracy. So this was sort of the our whole setup, but when we started this project, the idea that we had was, well, in a way, we have access to this these LFA tests, but we also have access to a lot more information in a way. And in particular, we have access to geographical data on where the sort of the candidates are, the personal information, these tests, questionnaire data on, for instance, their symptoms, their, what's, their exposure risks, etc. And so all of these sort of other sources of information, in a way, by themselves are only weakly informative. Like symptoms themselves do not tell you a lot about, whether you have COVID or not, because the symptoms are not highly specific. But the idea is that, maybe, so each of them is a weakly informative data source, but if you take them in combination and try to combine them in a, in a proper statistical framework, then in that case, you might actually be able to improve the accuracy of your diagnosis. And so the idea is really to take these weakly informative sources and combine them whilst accounting as well for their corresponding levels of uncertainty. The second thing that we wanted to do is, in order to give like an answer, in order to say, for instance, to someone, well, given your symptoms, given your antibody test results, like what's the good outcome? So what we thought would be, instead of having a yes or no answer, what we were really interested in is, first of all, well, the probability, right? It's the posterior probability. What is your probability of having COVID or having had COVID, given a set of symptoms and a test result? And along with a measure of the uncertainty associated with that diagnosis. So again, since we're here trying to combine weakly informative data sources with high amounts of variability, we actually really wanted to put an emphasis on trying to quantify that uncertainty. Finally, we're also dealing, potentially we're, in a medical sort of realm. So especially if you're dealing with questionnaire data, we also wanted to be able to have an algorithm that would be amenable to the handling of missing values. It typically plagues medical data. So our idea was, in a way, to try to leverage, the practicality and, the ease in terms of logistics of potentially weakly informative tests, and to combine them with other also sort of cheap data sources in order to provide a better and hopefully more informative computer-aided diagnosis of COVID. So this was our sort of general idea and sort of when we created the team. So in terms of the timeline, so the team, we actually started thinking about this a while ago in spring 2020. And what happened actually was that Freddie got in touch with a team of doctors in the UK who were trying to do pretty much the same. So what they wanted to do is address questions regarding to quantify, first of all, the robustness of the antibody response, so immunity, because they were trying to study immunity for COVID. And so they wanted to try to see how robust this antibody response was and how long it lasted. And they had a setting, using LFA kits, actually. So these at-home test kits that, participants in their study would use to repeatedly test themselves. And they also had questionnaire information. So we prepared up a little bit with them in order to be able to develop our, our method and try to test it to make sure that it was sort of useful. But in October, so that was until the end of the summer roughly, but when we saw in October the C3I Grand Challenge, we actually saw it as an opportunity to try to take our method further. So what we had was an algorithm that was sort of tailored for antibody response, immunity studies, and with the wealth of information provided by C3I, we actually saw this as an opportunity to try to expand our method further, to make it more useful and to try to provide, for instance, answers as to current status of immunity, and also develop it further into something that would look more like an app and that would be more readily usable by anyone, actually. And so, and then we submitted pretty much at the mid-November. So that's just to give you a little bit of background on why we wanted to tackle this problem and our timeline. So in this talk, I'll start by explaining roughly our method. So that is a Bayesian network for heterogeneous data integrations for medical diagnosis. And I'll go on in the second part with maybe the more specifics to the C3I challenge and how we sort of built this method into a pipeline that is readily, is able to readily give results to individuals if they wanted to check their COVID status. Okay, so let's start with first a little bit on the methods. So Bayesian Network for heterogeneous data integration. So that was our proposed solution. Perhaps to understand why we chose a Bayesian network, well, it's useful to put it in context of the entire field. So AI applications to medical diagnosis. So there is, I'm sure you all know that there's a huge sort of enthusiasm for AI and its application to medicine. But maybe you could say that, especially recently with the development of deep learning, etc., a lot of the emphasis has been put on trying to use AI for single modality analysis. That is, typically AI is used in a very specific sort of, you could say, corner case, right? Where you have access to, the data only consists in a single type of data input. So whether these are maybe X-rays or scans, ECGs, etc. So a type of, in a way, data that has been often acquired by clinicians using specialized and highly accurate equipment, and often as well very expensive. But as a consequence, typically that data has a lot of signal. So these approaches do not feel the need to harvest the potentially rich and complementary sources of information provided by alternative medical modalities. The data set also has been labeled by clinicians, and because again there's high signal, typically we trust the label. So you could say that you have access to ground truth in a way labels, and you are able to deploy supervised learning approaches on these data sets. And finally, the other main thing is that they seldom include uncertainty quantification as part of the outputs. They're more focused on prediction rather than quantification. So given this sort of setting, maybe by contrast, ours is quite different. Well, in a way, as I said before, like we have test results for individuals, we have symptoms, etc. But none of these data sets by themselves is very informative. Like if you just look at symptoms, it's usually quite hard to parse and to determine who suffers from maybe just like regular flu or cold versus COVID, and for most cases, mild cases. It's also very, because we also don't trust the test, as I showed on these curves. The sensitivity highly depends on time, on the time of testing. So we can't really say that we have access to trustworthy labels. So this sort of pushed us to use unsupervised learning approaches, pretending that actually we don't have access to the ground truth label. What we want to do in this type of approach then is say that in a way what we're really interested in is recovering a latent diagnosis, if you will. So for instance, this diagnosis being, do I have currently COVID? Or if you're interested in immunity, did I have COVID, for instance, at that time? And so this is latent, this is hidden, but what we have access to is sort of manifestation of like sort of variables that are correlated, dependent on this status, right? So your symptoms, if you had some, and the test results. And so the idea would be to try to combine all of this to try to recover this latent diagnosis using a generative model, so the Bayesian network, to do this recovery. And what's particularly interesting about these Bayesian networks is that they also allow, because we're building this generative model, we're saying how variables, random variables were generated, one as a consequence of the other. We also have to put priors on the distributions, and this is where typically it's very easy to add any type of prior information you might have on the topic, right? And to pool information across modalities to recover the latent diagnosis. And finally, these Bayesian methods are also typically a little better to work in low sample regimes. And then, which typically, we're going to face compared to, traditional AI approaches that have data sets with, tens of thousands of cases. So this is, in a way, why we chose to go through the unsupervised Bayesian way. So this also required, to tailor this approach a little bit. So, Bayesian networks have been used for computer-aided diagnosis before. In our specific projects, we had to tweak it a little bit compared to maybe more standard approaches. In particular, because compared to most applications of these Bayesian networks for diagnosis, actually, we were confronted with more uncertainty than in any other setting. So that is, especially when we started, the etiology was not very well characterized for COVID. The symptoms are not very specific. We also wanted to integrate risk factors and geospatial prevalence data. And all of this, in a way, ended up, for us, having to deal with a model that, where the uncertainty landscape was greater than for any other types of approaches, and we had a deeper hierarchical network than most what we had seen in literature. And as a consequence, we had also to adapt a little bit our way of solving for the different parameters. So perhaps to give you a more visual take on what we were trying to do. So this is like a schematic of the Bayesian network that we wanted to implement. So at the center of the screen here, that's the true diagnosis, right? The one that you don't have access to and you would like to infer. What this diagram shows sort of in the center box is, in a way, so in gray is all of what we can observe. So you have a certain set of risk factors. So this could include, for instance, where you live, what's your occupation, what's the number of people in your household. All of this sort of influence your probability of having COVID. So that's the true diagnosis. You can't observe it. Based, conditionally on having COVID, for instance, you can develop symptoms. And in that case, you have a number of symptoms that you can choose from. So cold, flu, so feeling, the chills actually, the flu, the fever, sore throat, et cetera, et cetera. And you, independently of these symptoms, you also have the test outcome if you were to take a test. So that's only contingent on your, dependent on your diagnosis and time of testing. And so that's the center box. And pretty much on the outskirts of this box, you have all the priors that we needed to put. So basically, the idea is that, in the setting, we actually don't know, we have a lot of uncertainty on the symptoms distribution themselves. Like, it's hard to say what's the real, for instance, prevalence of, sore throat is amongst people that have COVID. And so to model a bit this uncertainty, what we're going to say is that this probability is itself comes from another, is a sample from an overarching probability distribution, and which is parameterized by these hyperparameters. So it's a way, if you will, we're capturing the uncertainty in our knowledge of how the symptoms work and their prevalences in the population with these additional random variables. So basically, what we have to do then in our model is recover the true diagnosis. That's what we're trying to do, but we also have to fit these this uncertainty distributions, if you will, these priors through on our data set. So so basically the ingredients of our network is, first of all, we have to choose a prior, like how we're going to parameterize, for instance, the distribution of the prevalence of people suffering from, sore throats if they have COVID. For this, in particular, in this application, we chose to use what we call conjugate priors, which is it's a very specific type of prior in each case. The main thing that is worth mentioning is that this was for ease of computation, but our method was sort of made so that it's by no means restrictive, and you can sort of input any type of prior you want if you think you have a prior that seems more reasonable to you. In terms of the hyperparameters choices, which in a way serve as a way of warm starting, if you will, your warm starting your algorithm, we chose hyperparameters from existing studies or uninformative beta priors if we had no information. And I'll come back to it a bit later in the talk, but that was one of the main advantages of this method, is that it really allows you to use the expanding literature and the expanding knowledge on COVID to always try to improve your algorithm, your outputs, and make it more robust against sampling bias. So so that's pretty much, we sort of built the black box, so our Bayesian network, and now we have to fit it. And particularly to try to fit it and recover, so both the posterior distributions for the symptoms and the diagnosis. what we did is use a stochastic expectation maximization algorithm. So the stochastic expectation maximization algorithm, or stochastic EM, so it's just a simple tweak on the more traditional expectation maximization algorithm. So for those who don't know what the EM is, it is a very standard way in solving, well, sort of models like this, generative models like this, when you're trying to uncover latent variable based on observables, and it proceeds in an iterative fashion. And so you start by sort of computing the expected value of your missing variable, and you use this expected value as a way of inferring, of maximizing the likelihood and computing the parameters. Here, it's a little bit different. So it's pretty much, it follows the same steps. So the first step is an expectation. So you pretty much, for instance, here compute the odds ratio of the posterior of the hidden diagnosis variable. So the ratio of, diagnostic being 1 given the parameters and the symptoms, the risk factors, etc., over the probability of being negative for COVID. But instead of just using that expectation to try to maximize and optimize the parameters, what you do is a sampling step. So the idea is in here, you're really trying to find a way, a principled way, if you will, of imputing the missing values, the missing D, that are necessary for you to optimize then your parameters in the whole distribution afterwards. So basically here you sample and then you compute this maximization step. So the output from the stochastic EM is a sample from a stationary distribution whose mean is close to the maximum likelihood estimate for that particular variable, but whose variance reflects the information loss due to the missing data. So that's the general idea. And so this is not a novel algorithm, but it has some interesting properties. And in particular, it's been shown to be more robust and less dependent on parameters initialization than EM, which was a definite advantage in our setting since we were confronted with a lot of uncertainty. And so we really wanted to be able to have some notion of guarantee against dependency on parameters initialization. It's this stochastic EM also has been shown to exhibit a better asymptotic behavior. So because actually in that process, because every time you're sampling, instead of using a pseudo score as a way of imputing your missing value, you actually in the M step are always maximizing the complete log likelihood. And so typically this has been shown to have better convergence, better asymptotic behavior. And finally, this was also a way of providing us with extra flexibility and carry out inference if we wanted to with priors that are not necessarily the beta distribution. So it provides you with more flexibility in general. So this was our reason for choosing this type of approach. So now that we had a way, we had built our model, we had a way of fitting it. The only part that was missing was a way of, actually evaluating it, right? So that's sort of the last step in any ML type of approach. So here, because we're in a supervised setting, like in the supervised learning realm, it's a little bit difficult. So what we started with was actually evaluating out on synthetic data. So we tried to recreate synthetically like a setting, a set of experiments that would be sort of mimicking what you'd expect in real life. So for instance, we generated symptoms and test results with a little bit of noise and risk factors, etc. And we controlled all of these distributions. And basically the idea was to try to deploy our algorithm on this synthetic data set in order to assess whether the recovery was successful, how much it's actually yielded as an improvement over, for instance, using each of these sort of modalities, so whether just the test or the symptoms by themselves, and how accurate, what was the whole process in general. So this is what we did. These are a few plots from our experiments. So first of all, we started by looking at, so first of all, the added accuracy that the combination of the test plus symptoms would yield in this sort of controlled setting. And as you can see on the table here, well, for values of the sensitivity and specificity that's sort of are within the realm of what we'd expect in real life, this can actually lead quite substantial accuracy improvements, so up to 16%, for instance, here. So that was already reassuring. So we had an algorithm that, you know, could actually, for which the combination of two weakly sort of, you know, noisy observables was actually, you know, made a difference in terms of recovering the latent diagnosis or the latent state. So having COVID or, you know, not having COVID. The next step for us was to try to actually assess and try to study the properties of this algorithm in terms of the robustness to low samples. So as you can see here in plot A, we also looked at various levels of noise, especially in the risk factors, right? So it's basically a logistic regression, right? But what if we introduce more and more noise? How does this affect the recovery? We also compared it with other versions of the more traditional versions of the EM and some vanilla classifier, for instance, that would just based on the symptoms in the test try to learn the diagnosis. And we sort of showed that actually in this very controlled synthetic setting, our stochastic EM approach was actually uniformly sort of better in terms of recovered accuracy. So that was very reassuring for us. The next step for us was actually, so we were partnering with this, as I mentioned, with this team of doctors in the UK. And so they had real data. And so we actually tried to deploy our methods on their data to try to see if the algorithm could especially help trying to flag false negatives. That was our main sort of approach. And so here in this panel, I've shown some outputs of, you know, for some of the patients. So first of all, in panel A, for instance, and B, you have instances where on the left, you always have the distribution of your probability of having COVID or not having COVID based on just your symptoms. So typically it's a bit wider in terms of the width of the distribution. But what's interesting is, for instance, in A and B, pretty much, you know, the test and the symptoms concur, and so it yields, you know, sort of very highly confident results, diagnosis, right? The standard deviation is actually quite narrow. Sometimes though, this is another case, like for instance, in subject 7 here, you have a subject who typically had a lot of COVID-like symptoms. So potentially he had symptoms that are quite characteristic, like for instance, loss of taste or smell, but then the test didn't concur. And so what happens is that in that case, you get a distribution, you know, that has a very large, you know, standard error. And we sort of try to use this as well to, first of all, check, you know, these patients and make sure that, you know, that wasn't a correct flagging, and well, to sort of, you know, automate the process of finding these potential cases, so false negatives. So yeah, so that was pretty much our idea, and I know we also we published the approach as part of the ML for Health workshop in Europe. So yes, that was sort of the first stage of our project. In the second stage, so it was more about, well, this is when we registered to the C3I challenge. We really tried to push this a little bit further and make it maybe less, well, more accessible to all, and try to build an app, so which came with its own set of challenges. So indeed, so when we found out about the C3AI competition, what was particularly interesting for us was the fact that, you know, the C3AI was actually providing huge data resources as part of their COVID data lake. And they also provided tools that made it very easy to query from all of these data sets. So it really provided us with, you know, everything we wanted, and made it much easier for us to actually try to build a pipeline that would sort of allow people to input just their test results and symptoms and provide this diagnosis as an output. So in particular, yeah, what we were interested in is, we had done, we had started a project and we had teamed up with a team of doctors in the UK that were very keen on studying immunity, but we really thought that it could be also interesting to just apply this type of approach for COVID, sort of testing, like rapid testing, if you will, and not determine necessarily your immunity, but really your actual current risk of being infected, especially since, as the pandemic goes on, more and more of us have had situations where maybe you've had symptoms and you're almost sure you have COVID, but then the test comes out negative. And when you see, for instance, the curve on the difference, the graph on the right, so that's actually a plot from a study of the sensitivity of actually the probability of being negative if you have COVID from RT-PCR, and you see that this sensitivity is again like for LFA tests and for antibody tests that we had, is highly contingent on time. It's never 100. You also never have 0% of being called negative if you actually have COVID, right? At best, the best time that you can take the test is maybe 4 to 5 days after symptom onset. So here on the x-axis you have the days, and the dashed line from the study represents fixed symptom onset, so 5 days after infection. And you can see that at best, if you take the test 4 days after, you actually have roughly only 20% of being falsely classified as negative. So in any case, so this shows that in this setting, there's also a need to try to improve the accuracy of these different tests, potentially through the combination of different alternative data sources, and to be able to quantify our uncertainty on the diagnosis a little bit better. And so the other thing that we really wanted to focus on was trying to leverage also all the pipelines of C3I to try to make something that was neater and convert our algorithm into a proper user-friendly app. Okay, so in particular, so what did we use here? So how did we sort of, extend this? Well, the first thing is that, among the C3I datasets, we were particularly interested by carbon health data. So it was a dataset that was actually quite similar to the ones that we had with the UK collaboration. That is, it consists in, well, you have, each line is a test actually, so from someone. So you have the test type, the symptoms data as well, risk exposure data. So is this participant from high risk occupation or not, etc. Did the participant have high risk exposure within like 3 to 4 days after before the test? And also you have, so most importantly, the number of days since symptom onset as well. So that's a key variable as well. So that was in a way a very, the format was the same as for antibody testing, but just for here, sort of actual, current infection testing. And the other type of information that we were really keen in trying to leverage was all of the data that we had in the lake on, so from John Hopkins on the current COVID cases, ECDC and New York Times as well. So they're all provided sometimes complementary, so so to get the best coverage actually across the world, and also data from the World Bank about population statistics. And this is actually quite essential in trying to, I'll come back to it in a second, but in trying to determine some of the input variables that are crucial in the model. Finally, we also added on top of that additional information. So typically from either additional public data sets or from published studies and meta-analysis, etc., to try to a bit warm start again our sort of black box algorithm to through this choice of hyperparameters. So yeah, so just to make it a bit more visual, again, so what we had is this data set that we wanted to well, this model that we wanted to fit on the data set, on the carbon health data. So carbon health data in a way gave us all of these grayed out variables here, so symptomaticity, symptoms, test outcome. And what we're again trying to recover is this true diagnosis. The risk factors, some of them were in the carbon data sets, but for some of them, like for instance, the prevalence, well, it's actually not readily available. So you have to compute it, right? So this is where the additional data sets were handy. We also had to, again, choose all of these hyper parameters for the symptoms, distributions, and the sensitivity, specificity. So that's also through published studies. So yeah, so in order to pick, so let's start by perhaps the like one of the most simple things. So we needed to pick the different priors, to pick values for the hyperparameters of our distribution before fitting it. And this for this we used meta-analysis, published meta-analysis. So this we thought was particularly crucial in this context because despite the wealth of data that we now have, because as the pandemic goes on, we actually learn more and more about the data. You also have, as a consequence, an enormous amount of different studies studying the same thing and yielding different answers. So it's very hard to actually know which study to trust and which result to pick. So to give maybe a more concrete example, so here is actually something that I found on the blog on the web. But if you were to study a simple question, like for instance, what is the rate of asymptomatic individuals among the population, especially early in the pandemic, you basically just query all the published studies on the topic, and you could see vastly varying numbers that were being reported. So from 18, 50 to 75%, 31, et cetera, et cetera. So it seems that when you do this type of search, what you really learn is that, well, roughly, maybe to push the comparison a little bit, but you roughly learn that the prevalence of asymptomatic individuals is a number from 0 to 100%, and it's very hard to actually know more. Yes, it seems that this number is actually quite contingent on which study, the cohort that was studied, etc. So it's very hard to know if you want to to take something as an input to your model, which is the right case and which is the right sort of a study that you should consider. So a solution for this is pooling across studies. So using many meta-analysis, so that we found in order to try to maybe lessen a little bit, dampen this study bias that we could find, and find something that would be more suitable. The second main hurdle to our approach was trying to compute reliable input estimates of the prevalence, especially in the early days of the pandemic when there was a huge testing bias. So the idea is that you have a registered number of cases, but actually we have a good hunch that there might be a lot, like many more in the population, because because the testing availability sort of was not enough to cover the actual needs of the population, and so we actually might be missing a lot of cases. So we tried to correct for this by using estimates of the infection fatality rates and trying to correct the prevalence through these using these, which were supposed to be a more stable metric, right, less dependent on testing availability. And so that was the two hurdles. So I'm gonna
we have a live question coming in, and I missed it a minute ago. It was just about your first section that you were discussing here. Are the priors uncorrelated, and is that a simplification of the model?
Yes. So in the priors here that we choose them to be uncorrelated. You could say it's a simplification, especially, so basically, especially here, so the symptoms here, we made the approximation of saying that they were independent, conditioned on being symptomatic. So conditioned on the diagnosis. That is, once you're COVID you're positive for COVID, your probability of developing a cold, probability of developing like a fever, chills, sore throat, etc. They're all independent of one another. They're just dependent on the fact that you have COVID. That's a simplification, because you could say that indeed there are profiles of patients, right? So you typically symptoms are correlated. If you have a sore throat, you might have a dry cough or something like this. We found this approximation to make things simpler, but it is definitely an approximation, right? So you could say that in a way to extend this method would be to say, well, in a way here, instead of making two groups, right, the symptomatic people and the the asymptomatic people, sorry, You could have, an assignment to a group of symptoms, right? You could have, people that, for COVID develop just a mild sore throat and a cough, and then the others that develop, loss of smell and, achy joint muscles and so, things like this. So it is a simplification in this. And similarly, the choice of the priors is always done independently of one another. And yeah, it's a small, we thought it was a small, but at some level it may be necessary for the moment and justifiable approximation. So yeah, so let me just look, just a quick look. So basically we have packaged this into an R-Shiny app, so you can find on the web. So here is, I put the most recent link, so you're welcome to try it out. We're always trying to, we're continuously working on this, and we have, there's 3 of us, and it's a lot of engineering process, and so it's more like a side project. So if you find a bug, please do let us know, or we're trying to really improve on it, and in particular, so what we want to do going forward is, well, first of all, trying to robustify the method and improve it by finding new sources of data, right? Just trying to broaden a little bit the carbon health data in particular. We also want to try to find maybe even better ways of computing these estimates of the prevalence, and especially for, well, we have many problems, but one of them is test under assertment. So we had a fix, but we're always looking for better ways of doing it. We also have problems in that some certain countries either don't have many deaths yet, or anyway, that's not a problem itself. It's just a problem for estimation. So we're trying to work on these methods, and going forward, we're also very interested in actually using this. So we have shown we have to sort of package this into an app, so that's, we hope, somehow useful for the individual user. But we're also trying to use this more on the global level, if you will, to inform downstream analysis. In particular, what we're hoping is that with these individual estimates of the probability of having COVID, we actually are able to capture perhaps a little bit more the heterogeneity of like in the population, in terms of not just quantifying people by having COVID, not having COVID, but also we're trying to incorporate their prior risk, etc. And using this for trying to look at if we can use this heterogeneity in a way to inform pool testing or event risk estimation. So yes, this concludes my talk. So here, pretty much what I've tried to present was our statistical framework for trying to combine heterogeneous data into a more accurate COVID diagnosis. In particular, so with an emphasis on what we're trying to leverage is geographical data, self-reported symptoms, and demographic variables in a way. And yes, we'd like to thank the C3I Grand Challenge a lot. I mean, they're, well, first of all, we'd like to thank you for the prize, but they have also the tools that they put to our disposition were actually extremely useful for us to make any progress. So that was actually very great. That was an excellent resource. And yeah, we'd also like to thank the Digital and Transformation Institute for this invitation and our host. And yes, on behalf of the team, thank you very much.
Thank you so much. We have some time for questions, and I see the first question already came in. Actually, 2 already came in. Claire, a question for you. What are the priors and posterior that you use for this analysis? Also, is the source code available online?
Yes, the source code. So first of all, yes, the source code is available online. Yes, I might. Yeah, I put everything. So the submission, the C3I challenge actually required us to provide the code. So it's on GitHub. I haven't put the link, but I believe if you go on the Shiny app. There is a link where you can actually see all the information. Like there's a sequence of a hyperlink that will make you able to find the source. Second question. So basically the choice of the priors. So here, as I mentioned, so maybe if I can, I don't know if I'm screen sharing again still. But
no, you're not at the moment.
I'm not. Okay. Well, the idea is that when we're basically what we have is, for instance, we have a set of symptoms. Like, suppose you take one symptom, and you basically want to try to choose the prior that you have on that symptom, because a symptom is a Bernoulli variable, right? So it's just encoded 1 or 0. Do you have or do you not have the symptom? What we chose was well, just a better prior actually on so the symptoms is modeled as a Bernoulli distribution. The conjugate prior is a beta distribution in that case. And so this is what we used just to model everything. Again, you'd be able to find to fit, to extend our methods and to use other types of prior quite easily. But it just like this choice of prior, this choice of like, using conjugacy as a way of defining our priors was, well, made it very easy for us to, quickly derive the updates and just eased up a little bit the computational burden.
Thank you. What we can do, Claire, is we can put a link to the Shiny app on the Digital Transformation Institute website next to this talk, so people can find the source code there. We can coordinate that. Next question that came in is, hi Claire, could you say a word about if and how the missing data, for instance, a missing test result, can be imputed with the STM?
Yes, so I guess in that case, you'd have to go sequentially, right? Because basically, if you have that missing data, you have to add an extra step where you impute in a way these missing variables. You want to impute the test and the diagnosis in that case, for instance, at the same time, right? So these are in a way latent variables that you recover. And so in that case, well, the STM would work well, sort of similarly, except you'd have to in a way sample both the diagnosis and the test results as a way, similar, sort of simultaneously as part of your stochastic step, your S step.
All right, we have another one coming in from Hao Chen Chen. How much is the synthetic data used in the experiment similar to the real world data, and how to evaluate their reality?
Yes, so as I mentioned, so this is an unsupervised learning approach. So what we thought was, like the whole point is that we didn't trust the test labels. So we started by, so basically to set up the synthetic experiments, what we did was the following. So we knew that the real data, for instance, consisted in terms of like 3 risk factors, and for which we assume the distribution that seemed likely, and then 14, for instance, different types of symptoms. And what we did was like, we're going to sort of do the same, right? We're going to generate mock risk factors. We're going to generate, basically the entire, we took the pipeline. We say, risk factors determine diagnosis. Diagnosis determines, whether you're symptomatic or not. If you have symptoms, then you have then you have any symptoms, then, do you have the cold, yes or no, etc. And so we generated this in this particular framework, but we fixed in a way the true distribution of these symptoms, of these diagnostics, etc. And we try to in a way, now that I have my whole generation, sort of my whole pipeline, and I actually know the ground truth. If I pretend that I don't see it, how well am I able to recover it? In a way, this synthetic experiment is a little bit like a statistical petri dish, right? You're creating very, well, perhaps favorable conditions, but conditions that you control a lot in order to be able to assess and measure, quantify how well you're doing without being too much in the dark. So that was the first step. And then we sort of, once we were sort of reassured that on synthetic data, our method was able to work correctly and perform, give the results that we'd hoped for, we then deployed it on so first during the summer, so this immunity study, and to make sure that it sort of what we were saying sort of matched as well what the doctors would think typically, or if it was sort of any use in trying to flag the potential false negatives, which it seemed to be doing very well. So we were sort of happy with the performance of the algorithm.
Thank you. Another one coming in. Also, did you impute the independent variables? If so, what methods did you choose?
Yeah, so that's part of it. So it depends on what independent variables. So we have, so I suppose when you say independent variables here, you mean the risk factors, because in a way, what we have here is to determine, in a way, if you were not to observe all the symptoms in order to test, what you try to say is, what risk factors how can we link them to the underlying diagnostic with, for instance, logistic regression, right? And so here we have actually independent variables. So it's a mix actually. So some of them are observed because they're part of the questionnaire. So for instance, we've used things like, do you have any other person in your household, or in the case of the carbon health data, do you have do you work in a high exposure risk occupation, so, things like this. But we also have this the main not the main, but like one of the most important that we thought was the actual prevalence, in a way the local prevalence rate, that is in your area. So the granularity that we chose was actually the country or the state in the US, because actually, when you go into a little bit more in the details on how to estimate that, so that's actually a little bit tricky, as I mentioned before, because you have, this test under a certain bias, and you have to make sure that the data is of good quality enough, and so this you have to impute, right? So again, we couldn't go as far as maybe the county or the neighborhood level, because we thought that the data wouldn't be able to allow us to pretend having that high of a resolution. But yeah, we basically that's the one thing that we had to impute. And so this we did using the Johns Hopkins data, the ACDC, as well as the New York Times. So all of these sources combined helped us sort of provide a good coverage actually of all the countries and states across the world.
All right, with that, it seems that we came to the end of all the questions. Claire, I want to express a lot of gratitude. Thank you so much for sharing this talk. Also, of course, to your teammates, Freddie and Nina, who were on standby during the call in case any additional questions came up. With that, thank you for attending the C3I Digital Transformation Institute Colloquium series. Don't forget, next week, the symposium. Please take a look on the website for more details around it. And thank you so much.
Thank you very much.